Hi everyone, I hope you're all doing great. And today, let's look at the concept of transitive closure in graphs. So, before we learn about transitive closure, I think we are all familiar with the concept of adjacency matrix. So, let's look at that first. For example, if we have a basic graph like this, for example, if you have a simple graph like this, we can say that the vertex 3 and vertex 1 has a direct edge between them, and vertex 1 and vertex 2 have a direct edge between them, and the vertex 2 and the vertex 4 have a direct edge between them. So we can denote how these vertices are connected to each other with the help of an adjacency matrix. So how does this adjacency matrix look like? If we have 4 vertices, we can denote it with the help of a 4 by 4 matrix. So how is that going to look like? It's going to look like this. So let's fill in the values one by one. We are going to see if the matrices on the left side on the x-axis have a direct edge to the vertices listed on the y-axis. So for example, is the vertex 1 reachable from the vertex 1? Of course, because it's the same vertex. Obviously, we should be able to reach it. So let me put a 1 there. Does the vertex 2 have a direct edge between 1 with 1? Yes, it does. And if you observe closely, you can reach 2 from 1 and not 1 from 2, because this is directional and you are able to reach 2 from 1 with a direct edge. That is why I'm going to put a 1 here again. And if you look at the vertex of 3, there's a direct edge between them, and you can reach 3 from 1 because it is directional. So I'll put a 1 again. But is there a direct edge between 1 and 4? There is no edge. So I'm going to put a 0 here. Let's come to the second vertex. Does the vertex 1 have a direct edge from 2? Yes, it does. But if you observe closely, it is directional, and if the direction had been like this, we would have put a 1 here, but the direction is in the opposite direction and we cannot reach 1 from 2 directly. So I'm going to put a 0 here. And if you consider the same vertex, we are always going to be able to reach it. So I'm putting a 1 here. Now we have to ask, can we reach 3 from 2 through a direct edge? No, we cannot. So I'm going to put a 0 here. And coming to 4, is it directly reachable from vertex 2? Yes, it is, because we have a vertex, we have an edge which is properly directed. Now let's come to the vertex 3. Is the vertex 1 directly reachable from vertex 3? No, because the opposite is, the direction is in opposite. Is the vertex 2 reachable from 3? No. Is 3 reachable from 3? Yes. Is the vertex 4 directly reachable from 3? No, not again. And coming to vertex 4, is the vertex 1 directly reachable from 4? No. Is the vertex 2 directly reachable from 4? No. Is the vertex 3 directly reachable? No. Is the vertex 4 directly reachable? Yes, because it's the same vertex. So we can see how we can form adjacency matrices and define a relation between the vertices and how they are connected with the help of edges. So this is how we write a basic adjacency matrix. So now let's look at transitive closure. So looking at the definition, given a Boolean n by n adjacency matrix M, the transitive closure of MTC is an n by n adjacency matrix when M of ij is equal to 1 if it is possible to reach vertex j starting at vertex I, Otherwise, m of I j is equal to 0. So basically, we have already seen what is an adjacency matrix. An adjacency matrix tells us if the vertex I is directly connected with vertex j with the help of an edge. But what transitive closure does is that it is a state of the adjacency matrix where the mij will be equal to 1 if the vertex j is reachable from I even through other vertices. For example, if you look at here, we know that the vertex 2 is directly reachable from vertex 1 because there is a direct edge. And if we look at the adjacency matrix, we will get to know that. But looking at the transitive closure, we will be able to know if vertex 4 will be reachable from vertex 1 even through other vertices. Even though not through with the help of a direct edge like this, we can still know if the vertex 4 is reachable or not from 1. So can we do it or not? We can go from vertex 1 to 2, 2 to 3, and from 3 to 4. So vertex 4 is perfectly reachable from 1, and hence if in the matrix the m of 1 to 4 will be 1 because we are able to reach the vertex 4 from 1. So let's look at how we can calculate this transitive closure with the help of adjacency matrix. Here we have already been given an adjacency matrix. So if we consider this, let us try and draw the graph for this. So if we look at the first vertex 1, it is connected to 1, 2 and 4, which means that, okay, let's take a vertex. It is 1 and the vertex 1 is obviously reachable by vertex 1 and vertex 2 is reachable by vertex 1. So I'm going to draw this. And we can see that the vertex 4 is also reachable from 1. So let me draw this. Coming to the next vertex, everything else is a 0 here if you observe. So I'm not even going to consider them. In the second vertex, only the vertex 2 and vertex 5 are reachable from 2. So 2 obviously is reachable from itself, and let's take another vertex 5 which is reachable. Next, vertex 3. Vertex 3 is only reaches out to vertex 3 again. So we can say that for now it is not connected. Thinking about vertex 4, we can see that 2 is reachable from 4 and 4 is reachable from 4 and 7 is reachable from 4. So there's a direct edge from 4 to 2, 4 to 4 and 4 to 7, right? So we'll take another vertex 7 and draw a direct edge here. Coming to the next vertex 5, vertex 3 is reachable from 5, vertex 5 is reachable from 5, vertex 7 is reachable from 5 and 8 is reachable from 5. So we are going to draw a direct edge from 5 to 3, of course from 5 to 5, and there's a direct edge from 5 to 7 and a direct edge from vertex 5 to vertex 8. Coming to next vertex 6. Only the vertex 6 itself is reachable from 6, so I'm assuming that it will be somewhere here, not connected to anything else for now. So the vertex 7, from vertex 7 we can reach vertex 5 through a direct edge, so I am assuming there will be another one like this, and of course 7 is reachable from 7. And if you observe here, the vertex 8 is reaching vertex 2 directly, so I'm drawing a direct edge like that, and of course 8 is reachable by itself. If we assume that the graph looks like this for this adjacency matrix, we need to draw the transitive closure for this. We need to calculate the transitive closure. Going back to the definition, to compute MTC of M, we raise M to the kth Boolean power such that k is the lowest value for which M of k is equal to M of k plus 1. So the method to calculate transitive closure is to take this adjacency matrix and multiply it by itself. And we multiply it and continue to multiply it so many times that the m power k will be equal to m power k plus 1. And we can reach a stage like that, then we will conclude that m power k is the transitive closure state of that matrix. So we have transitive closure here. This is the same adjacency matrix which we saw upside here. So we are going to write it down here, and here we will compute the value of m square. I hope you're all aware with the concept of matrix multiplication and how it's done. I'll just explain how the first few values are formed so that you get an idea. In matrix multiplication, we will sum the values by multiplying the first row and the first column to obtain the value at this position. So let's look at that. First we have the first row 1 1 0 1 0 0 0 0, and we are going to multiply these values respectively with these values 1 0 0 0 0 0 0 0, and we will add them together to obtain one final value which we can put here. So we are going to multiply this value with this value with this value. So we will get 1 into 1 plus, we have 1 here and 0 here, 1 into 0 plus, we have 0 here and 0 here, 0 into 0 plus 1 into 0 plus, and all the remaining are 0 into zeros, as you can see. So finally, we can see that we got at least one 1 here. So we can obviously put the value 1 at the first position. And to get the second position, we will multiply the values of the first row with the second column. And we will repeat these steps for the entire matrix till we fill the entire matrix. And that is how we will obtain the value of m square. It might seem a little tricky at first and that it's taking a lot of time, but if you can just see, even if there is a one single product that leads to a 1, we can just directly put a 1 there. So please be patient and cross verify these values if you want to. But if we multiply m with itself, we will get m square here, m square like this. And if we proceed one more step and calculate m cube, we will get this value. And if we go one more step again and we calculate m4, this is what we are going to get. But we can observe here that the value of m3 is exactly is equal to m4, and there is not even a single value that is different from each other. So here we can say that transitive closure has been achieved. And when we say that transitive closure has been achieved, we can tell which vertices are reachable from which vertices. So let me just quickly draw up the diagram, the graph we drew above. Okay, it's a bad diagram, but it will do for now. So let's look at the transitive closure matrix. So we will say that the transitive closure has been achieved at m3. Now looking at m3, let's just also write down these values. It's 1 2 3 4 5 6 7 8 and 2 3 4 5 6 7 8. Perfect. So now that we have these values, let's see what we can do. The whole concept of transitive closure is to see if we are at, for example, in this matrix, if we are at this particular vertex, for example, what is this? This is like m of 2 8, right? This one right here. So the concept is that to see if the vertex 8 is reachable from vertex 2 at least through other vertices, if it can be reached. So if we have any value here that is like m ij. All we want to know here is if the vertex j is reachable from vertex I or not. Let's cross verify that. Is the vertex 1 reachable from vertex 1? Of course it is. Is the vertex 2 reachable from vertex 1? Of course it is. Is the vertex 3 reachable from 1? Let's see. We can go from 1 to 2, 1 to 5, and from 5 to 3. Of course we can reach vertex 3. Can we reach vertex 4 from 1? Of course we can. Can we go from vertex 1 to vertex 5? Yes, we can. From 1 to 2 and from 2 to 5. Can we go from vertex 1 to 6? If you see, there are no incoming edges to 6 at all, and hence there is no way we can reach 6 from 1, which is why we have a 0 here. And can we reach 7 from 1? Yes, we can. That is why there's a 1 here. And can we reach 8 from 1? Of course we can. From 1 to 2, 2 to 5, and 5 to 8. So that is why we have 1s in all these places. Let's look at the second row. Can you reach 1 from 2? There are no incoming edges to the vertex 1, and hence if you observe here, the whole row here is zeros because nothing goes inside towards 1. But let's check each value. So you can't reach 1 from 2, so it's 0. You can reach 2 because it's the same vertex. You can reach 3 from 2. Obviously, you can go from 2 to 5 and then 5 to 3. But you cannot reach vertex 4 because a vertex 4 has an incoming edge only from 1 and you cannot reach it from any other vertex. So you cannot reach vertex 4 from 3, which is why there is a 0. I mean from vertex 2. So if you cross verify this like that, there is a 1 at this place only because this vertex can be reached from this vertex. So what I want to say is that transitive closure tells us which vertices are reachable from which vertices. If there is a 0 somewhere, we can without any hesitation say that the vertex j 6 here cannot be reached from the vertex I, which is 7 here. Is it possible to reach 6? No, of course not. That is why there's a 0 here. So that is the whole concept of transitive closure. It tells us which vertices are reachable from which vertices. To get the transitive closure, you just have to keep multiplying the adjacency matrix with itself until there is no change between two consecutive multiplications. So we have M3 here and M4 here, which are both just same, which means the transitive closure has been already achieved at M3. So I hope you got a good understanding now. And if you have any more doubts, you can always feel free to contact us.